In this video, I will show you how to run regression analyses in Jamovi. Let us first load our dataset. To run a regression, you need to go into this regression menu and choose linear regression. First, you need to choose your dependent variable. Let us begin with a simple example of a simple linear regression. Let's say you want to predict the children's word reading fluency in first grade from the children's letter knowledge in kindergarten. So you send the dependent variable here and the independent variable here to covariates. You can use categorical variables as predictors, and Jamovi will use contrast coding to treat this as a quantitative variable. In that case, you would have to send the predictor into the factors panel, and that will function as another predictor. In our case, we will just examine the simple linear regression predicting word reading fluency in grade 1 from letter knowledge in kindergarten. This is our coefficients table, but before we go on to interpret this, we need to check the assumptions. Click on assumption checks, and then examine normality by a Shapiro-Wilk test and the QQ plot of residuals, and also look at the residuals plot to examine homoscedasticity. We see that the normality assumption is not violated. We have a non-significant Shapiro-Wilk and a good-looking QQ plot. This is the plot of residuals versus fitted. This means predicted or estimated. So this is the plot in which you should examine whether the spread of the residuals is about the same across the whole range. And in this case, we do not see any reason to worry. There seems to be a fairly even spread, although it's not exactly the same. There aren't very many data points. So now we can go back and look at our results, and we can add additional measures of fit, such as the root mean squared error and the overall model test, the F test. This is the R squared, the proportion of variance in the dependent variable that is accounted for by the independent variable in this model. And this is the variance ratio test, which is statistically significant and tells us that this linear model is significantly predicting variance in the dependent variable. And moving into the results for the specific predictor, letter knowledge, we see that its slope is 0.664, and this is statistically significant. So it is different from 0, and we are predicting a change in word reading fluency in grade 1 by 0.66 words per minute for each additional letter that is known in kindergarten. The intercept for this prediction is 15, and this is the predicted word reading fluency in grade 1 for a child who doesn't know any letters in kindergarten. An additional piece of information that is often useful is the standardized coefficient. The standardized estimate for the coefficient under the model coefficients menu gives us 0.397. What is the standardized estimate? It's the slope for the standardized variables. It is the slope you would get for letter knowledge in kindergarten if, instead of running a regression for letter knowledge predicting word fluency in grade 1, you had run a regression for the z-score of letter knowledge in kindergarten predicting the z-score of word fluency in grade 1. You can actually try that and see that you'll get this slope. In terms of this analysis, what does this mean? Instead of interpreting the slope in terms of the actual measured units, like this one, the regular non-standardized slope is how many more units of word fluency, so how many more words per minute, a child is predicted to read if they know one additional letter in kindergarten. Now, the standardized slope instead is the same, but in terms of standard deviations. So instead of predicted change in word fluency given a unit change in letter knowledge, this slope is predicted change in standard deviations of word fluency given one standard deviation change in letter knowledge. What does this mean? It means the predicted difference in word fluency in grade 1 measured in standard deviations for a difference of one standard deviation in letter knowledge in kindergarten. In other words, the difference between two children in kindergarten, where one of the children is exactly at the mean, so a standard score of 0, and another child which is exactly one standard deviation above the mean, that's one standard deviation difference between these two children in letter knowledge in kindergarten. So these two children who differ by one standard deviation in their independent variable, how many standard deviations are they predicted to differ in the dependent variable? The answer is 0.397. So about 0.4. About 40% of a standard deviation is the predicted difference for two children differing by one standard deviation in the independent variable. Let us move on to a different case where we can use more predictors so that you see how that's done and how it's interpreted. Let us run a new linear regression. And this time, try to predict vocabulary in kindergarten from nonverbal ability in kindergarten, letter knowledge in kindergarten, and word reading fluency in kindergarten. And, well, why not? Also sex in kindergarten. This is a categorical variable. So it is coded by Jamovi into numbers. Let's first look at our assumptions. Shapiro-Wilk and QQ plot for normality, residual plots for homoscedasticity, and also collinearity diagnostics. Collinearity is a condition where your independent variables, when you have multiple predictors that are highly correlated with each other, this creates instability in the estimates, and it becomes difficult to say which of the predictors is actually affecting the dependent variable. In this case, we have low variance inflation factors. So VIF is the variance inflation factors. These are low values. These are near 1. If they're above 5 or above 10, these are worrisome. In this case, there is no problem because actually our predictors aren't very highly intercorrelated. Evaluation of normality is fine because we have a non-significant Shapiro-Wilk and a good-looking QQ plot of the residuals. And the plot of residuals against predicted also looks fairly even, so there are no reasons to worry about heteroscedasticity. This means that we can go on and look at and interpret our results. We can add the root mean square error and the F-test. Here we see the proportion of variance in vocabulary in kindergarten that is accounted for by all of these predictors considered together. So 27.3% of vocabulary variance can be accounted for by all of these together. And this is a statistically significant prediction, a statistically significant portion of variance, because we see that the overall model test through the F ratio produces a low p-value. So this linear model that we have produced here with all these predictors does predict significantly vocabulary in kindergarten. However, not all predictors are actually useful here. If we look at the individual slopes, these are the estimates for the individual slopes, and these are the p-values for them. We see that only the slope for non-verbal ability is statistically significant. Letter knowledge, word reading fluency, and sex do not seem to add anything to the prediction of vocabulary in kindergarten once you've already used the value for nonverbal ability. So these three are non-significant predictors and should be removed from the model if you're trying to come up with the parsimonious model. In this case, we have a significant prediction from nonverbal ability with a slope of about 1.4. What this means is that our predicted vocabulary in kindergarten increases by 1.4 points for each additional point gained in the matrices test, as long as there is no change in the other predictors. Put in another way, the difference, the predicted difference for kindergarten vocabulary for two children who have the same sex, equal word fluency, equal letter knowledge, and differ in the matrices test by 1 point, these two children are predicted to differ in vocabulary by 1.4 points. So that's exactly the same thing that, as we said before, phrased differently. That's the meaning of the slope. And the meaning of the intercept, this 34, is predicted vocabulary score for a hypothetical child that has a 0 value in each of these predictors. So 0 score in matrices, 0 letter knowledge, 0 word fluency, and 0 sex. And if you want to see what 0 sex means, you have to look at the reference level. So 0 is the child who is female, so a girl, corresponds to 0. Let's now look at a hierarchical regression. So you can see how you can use different steps to calculate the variance that is added by using more predictors in your linear model. Let's start a new linear regression. And let's try first to predict vocabulary in grade 2 from matrices, so nonverbal ability in kindergarten. Can you predict a child's future vocabulary in grade 2 by knowing their performance in the matrices test in kindergarten? So briefly, it looks like this is possible. We should probably not say anything before we look at the assumption checks. The assumptions checks are okay. So we can say that nonverbal ability in kindergarten significantly predicts vocabulary in grade 2. And indeed, for each extra point of matrices in kindergarten, we predict 1 extra point of vocabulary in grade 2. But how about if we already know someone's vocabulary in kindergarten? Does knowing their nonverbal ability help us predict beyond that? Conversely, if we know vocabulary in kindergarten, does it help us predict vocabulary in grade 2 beyond what matrices predict? So these are two different questions. We're going to look at both because they're done in the same way, but you have to make an opposite choice. So first we enter both variables in the model. We're interested in predicting vocabulary in grade 2 by matrices, so nonverbal ability, and vocabulary in kindergarten. At this stage, they're considered together. Our assumption check is barely okay, so it's not less than 0.05, it's just okay. And there is no substantial heteroscedasticity visible in this scatter plot. So we can see that we can account for 28% of variance in grade 2 vocabulary by these two predictors, although only one of them is statistically significant. So only vocabulary in kindergarten is statistically significant. Let's see what this means in terms of different steps. We can use two blocks for our variables. So now we only have two predictor variables, so it will be one in each block. But there is no limit to how many of your variables you can add in each block, otherwise known as each step. So step and block here is the same. Let's say we want to control for nonverbal ability in the first block. So our first model, we only use matrices. In the second block, we add vocabulary in kindergarten. So model 1, I'm choosing model 1 here, that has, for this dependent variable, only one predictor. Which one? The one that I entered in block 1. I could have entered more variables here. So if I wanted to control also for letter knowledge in kindergarten, I could have more variables in my first block. Now I've changed the model. I need to take another look at the assumption checks. Now we have a not normally distributed residuals. So this was probably not a good idea. And so we'll have to take this one out. So model 1 includes the variables entered in block 1. And we see that matrices in kindergarten is a significant predictor of vocabulary in grade 2. Okay, now on top of that, we are going to add block 2. So the step 2 variables, which in this case is just vocabulary. Model 2 then has both our predictors in. And in model 2, we see that only vocabulary in kindergarten is a significant predictor. How that's different from looking at them together, if you use the different blocks, the difference is here. So the first model accounts for 9.4% of variance in the dependent variable. The second model accounts for 28% of the dependent variables variance. And we see that the difference between model 1 and model 2 is a difference in R squared of 0.19. So 19% extra variance in the dependent variable is accounted by going on to the second step. The second compared to the first adds 19% of variance accounted for. And this is statistically significant. So the extra variance accounted for in step 2 is statistically significant. This means that vocabulary in kindergarten is statistically significant after controlling for nonverbal ability in kindergarten in predicting vocabulary in grade 2. If we did that in the opposite order, it would have to be interpreted accordingly. So now I have the same variables, so my model 2 is identical, but my model 1 is not the same, and the differences are not the same. Model 1 now has only vocabulary entered as block 1. So in the first step, I am predicting vocabulary in grade 2 from vocabulary in kindergarten. That is a statistically significant prediction and accounts for 28.2% of variance in the dependent variable. So that is model 1. And then in model 2, we also add the block 2 variables. So in the second step, we have 2 predictors, one of which is statistically significant. And model 2, we accounts for 28.4% of variance in the dependent variable. The difference between these two is the difference in R squared, delta R squared, between model 1 and model 2, and is a tiny amount of extra variance accounted for by adding matrices after you've already put vocabulary in the equation. And this extra variance accounted for is not statistically significant. This means that you should not be adding nonverbal ability to the prediction of vocabulary in grade 2 because it doesn't add anything if you already know vocabulary in kindergarten. You do not get any extra gain in prediction. And that is also indicated by the non-significant slope of matrices in the final model. So that is how you run a hierarchical linear multiple regression with different steps so that you can compare the amount of variance contributed by each step. This is most useful if you have some basic variables you want to control for, or if you have groups of variables that are associated with different constructs, and you want to see how much each of these accounts for in the prediction of the dependent variable. You can have multiple variables added at each step, and you can have multiple steps. You don't need to have only 2 blocks here. You can add new blocks, as many as you want, as long as you put at least 1 variable into each block. And that's how you run linear regressions in Jamovi.